All right, we're back for turbulent flow. And so instead of copying the first inviscid flow, we're going to copy our laminar flow so that a few of the things stay the same. Duplicate. And this will take a minute.
We're
Right.
back.
We're back. She copied all the way down here. It is really far away, but that's okay. And so if you look in here, we're just going to double click into setup since the mesh is still the same.
Yep.
Is it going to be double precision? And we're going to
Everything's
start it out.
And we'll wait for that to load in.
Yep. All right, we're back. It loaded. And we're going to go right into models and we're going to change it again. And now instead of laminar, you're going to do Spalart. And since it has turbulent down here, that's where we're going to use it. And we're just going to keep everything in here. I'm not going to touch any of it. Just hit OK so that it changes and we'll be good with that. And then we're going to go into materials, fluid, air, and change the viscosity one more time to about the original values. We're going to do 1.8 times 10 to the negative 5 instead of negative 2. And it's just to mess with our Reynolds number to make sure it's big enough for laminar flow. And then right into our boundary conditions, we're going to go to the velocity inlet once again. I set the velocity as 100 meters per second, which seems like a lot of overkill, but we really want that difference to be large. And
Yeah, if it's too small, the lines just appear on top of each other and it can't really show much when you do a graph.
Yeah, exactly. And then once you have that Reynolds number calculated, you get, I think that's 5 million.
About.
Yeah, it's like 5.5 million roughly. So very big difference. So everything should go well. And then everything else will be the same. The outlet, that'll be fine. And then the wall is still no slip.
Just make sure it is.
Just in case. You don't want this to go wrong after it takes 5 minutes to calculate. And then we'll go into our reference values, make sure that those update, which they have. You can see them right here. I can't highlight it, but it's the 100 and 1.8 e to the negative 5. And then methods, it's going to be the exact same as the last two. Don't need to look at that too hard. And then if we go into our residuals, they're all the same. I like to change the bottom one as well, just so that everything matches. And then we can go ahead and initialize.
Your initialization is still 25.
Yeah, it didn't change.
Doesn't change.
And now that that's done, go to calculation. It's still 1,000 iterations. And we're going to calculate. And this one does take a while. It takes longer than the other ones. But put it on here so you can kind of see that going. And then we'll see you in a few minutes. All right, we're back. The calculations are done. And then one more time, we're gonna go into the plots, go into XY plot. We already have our pressure coefficient done. We can plot that, and you see it looks a little bit wonky, but this curve is gonna be a bit steeper than the one for laminar.
Yep.
And it kind of just cuts off after it goes up. But that looks all right. We can close that. We'll plot the velocity profile. Again, 0 all the way across just because of the no slip condition on the cylinder wall. So that looks good. And then we can run, where to go? Ah, yes, report definitions. We can compute our drag coefficient, and it's going to be a bit smaller than the one for laminar, but that should be okay. It's going to be right down here. And then we can save that, exit out of here. And then wait for that to close.
It's going to take a minute to close, because of course. And then we're going to go to results.
Give it a minute.
And look at the contours and the streamlines.
And this should be all on it already, so we just have to show you. And then at the end of this video, we're going to discuss all of the results from like the graphs we have of the pressure coefficients on one graph. And so this is going to be our pressure contour. It looks a little bit different, but pretty similar still to laminar flow. You can tell evidence of the wake region right on the back end here. And then when you pull up the velocity contour, you can see that really defined wake region. And you can tell how fast everything is moving.
Yes.
And so that's what our velocity contour looks like. And then we'll add the streamlines. And here it is. It looks pretty similar to laminar, but all of the values are a lot higher than laminars. And so those are our streamlines and contours, and we can save that, exit out of here, and then now, once that exits out,
we look at our Excel values.
yep, and so we have everything plotted here. We have the inviscid, laminar, and turbulent flows. We have the velocities for all of them, and we have them plotted in Excel. Laminar and turbulent are overlapped on each other on the axis because again, it's just been 0 the whole time. And then if we scoot over, you have the inviscid, laminar, and turbulent pressure coefficients. Sorry, you're like, and then we have them all graphed right here. You can see the differences between them, and they all look pretty good. And then up at the top corner, we have the drag coefficients, laminars being the highest. And it kind of makes sense. You can see with the pressure coefficient graph, everything is just a bit weirder for laminar than it is for everything else. And so that looks good. And those are all of our values on all of our graphs. And this is Ansys Project 3.